we've already talked about one portal vein in particular, right? The hepatic portal vein. So the hepatic portal vein is special because with all portal systems, the main purpose is to somehow direct blood in a certain direction. All right, direct it so then, more importantly, as we direct blood, we can funnel it into specific arteries and capillaries. So portal veins, veins that begin in a primary capillary network, extends a pretty short distance, or even in terms of hepatic portal vein, pretty long distance, and end into a second capillary network without returning back to the heart. In other words, you have one capillary bed that you're bringing blood to in one organ, and then you connect that blood that went to that first organ to a second organ, and a second capillary in a second organ. Then you return it back to the heart. So the good thing about this portal system is this. So there's two areas where I want you to know it. One is in the hypothalamus and the anterior pituitary. And the second area is between the intestines and the liver, the hepatic portal vein. So the hypothalamus one, so here's our normal circulatory system. You go oxygenated blood, about 99% oxygenation, full of glucose, exits the left ventricle, goes through the aorta, goes to your target tissue, goes to the capillaries where you have nutrient exchange. Then it goes back to the vein and back into the right atrium. That's normal system. Now in a portal system, you have the blood going out of the heart, lots of oxygen, lots of nutrient. It goes to the capillary bed in one organ, and then directly to a capillary bed in a second organ before it returns back to the heart. Now, I want you to, again, with ours, right, I want you to kind of understand why this is important. It's important because this. You guys have seen how small the hypothalamus is. The hypothalamus is a very, very small area in your brain. Very nondescript little area near the third ventricle of your brain. So if we look at something as small as the hypothalamus, how much blood does it receive? Not a lot, right? It's a very small area of the brain. So it's not going to receive a large amount of blood to begin with. Now what if I'm directing from the hypothalamus, I'm going to release hormones that need to go to the pituitary gland. And we're going to see that there are a lot of hormones that are released by the hypothalamus that then causes the pituitary gland to then release another hormone. An example, right? You guys have all heard of thyroid hormone. Now, in this class, in most classes, there's a lot of females in our classes, so at least one, either you or your family member, it's very close, has a female family member that has a thyroid condition. Thyroid conditions are very, very common in women. Yeah, there are a lot, right?
And then she lose weight,
and she's got hyperthyroidism, and her eyes pop out, right? We call it exophthalmos. Now, why am I mentioning this? Well, the thyroid hormone is released by the thyroid gland, but it's under the discharge of and by the control of the pituitary gland. So the pituitary gland releases thyroid stimulating hormone, which then causes the thyroid to release thyroid hormone. Now, in order for the pituitary gland to release that hormone, it needs to be directed by the hypothalamus. Right? Now, the hypothalamus, so let's say you have low thyroid hormone, and now you're out of homeostasis. You need to release more thyroid hormone. The hypothalamus is the one that starts that process. So the hypothalamus causes you to release a hormone right here, and then you release it into the bloodstream. That hormone then directly goes right into the pituitary gland, right? As it goes to the pituitary gland, all of that hormone from the hypothalamus, all of it, goes to the pituitary gland. There's no loss of signal because we're directing that blood flow from the organ, hypothalamus, then it goes to the pituitary gland right afterwards. Now you can imagine what would happen if I release, the hypothalamus releases the hormone and it's not part of a portal system where we have two capillaries connected to each other. What happens is this, you have low thyroid, now you get that signal from the hypothalamus. the hypothalamus releases a hormone. It goes back to the heart. How much of that signal then goes to the pituitary?
No.
Very little, right? Almost none of it would go, because very little will actually go to that small little gland that's found in the base of your skull. So what we do with the portal system is that we amplify the signal. All of the hormone that is released by the hypothalamus, all of it, goes through a second vein into a second capillary. Then it returns to the heart. That way, all of the signal from one organ goes to that second organ. So then there's no loss of signal at all. Now you can imagine just how small that blood flow would be, right? How small the signal would be if I had to kind of release it here, then it goes back to the heart, then it goes back to the common carotid, then how little of that signal actually then gets to the pituitary. You would lose almost all that signal, right? By attaching those two regions together by a portal system, we can then amplify the signal tremendously. So again, same thing with the hepatic portal vein. You've just eaten, and remember, keep in mind as we're kind of going through this, that our bodies are not always made, and hasn't been made, for continuous eating where we kind of know when our next food is coming. So that's one of the reasons why it's so hard to lose weight. That's my excuse anyways, right? So what happens? What happens is when you eat, you'll have a tendency to overeat as a result. Why? Because you don't know when your next meal is coming. You want to eat as much as you can and absorb as much as you can. So if I'm absorbing as much food as I can through my superior and inferior mesenteric veins, where's the next organ I wanted to go to? The liver. The liver is the one that produces fat from all of the carbohydrates so that I can store it for the future. The liver is the one organ that receives all the glucose and turns it into glycogen for the rest of the body to use. Any excess glycogen? Well, you know what happens? Well, some of that glucose gets turned to fat. The liver receives amino acids and turns it into albumins, turns it into fibrinogen, all those clotting factors that the body needs. So the liver then makes sense. We're going to direct all that nutrient-rich blood from the superior, inferior mesenteric veins into the hepatic portal vein. And now all that nutrient-rich blood gets to the liver first. As it gets to the liver first, then it goes to the heart. That way the liver always gets first dibs out of any food that we ingest. That way, any food you ingest, you go right to the liver, you store it for the future. Because you never know when your next meal is coming. We want to store as much as we possibly can. Now, so in terms of the portal system, when you guys get confused, review these right here. It kind of explains what we mentioned with that portal system. Now, hepatic portal system, again, with all these portal system, is a direct connection between two organs. Blood goes from one organ to the next before returning to the heart. And usually it's a way to make sure that we have a lot of that signal, a lot of nutrients that we can give to that next organ, the second organ. Right, so here the hepatic portal system, the hypothalamo-hypophyseal portal system, the concept is always the same. We're trying to redirect blood flow before it returns to the heart. And probably the easy way to just kind of even mention it is two capillary beds connected to each other in two organs, and then it goes back to the heart. Now, the next one is this, anastomoses right here. Now we should have, there's two types of anastomoses. There's an arterial anastomoses, and there's a venous anastomoses. The ones that are good, the ones that are a little bit more helpful, are the arterial one. And I'll show you guys again in a second about the portal system one. But in terms of the anastomoses, the arterial one are different connections right here. So if you have, think of the circle of Willis. If you did not have the anterior communicating, if you did not have the posterior communicating, if they were separate, what happened if there's a clot in any of the arteries, we'd be screwed, right? Any kind of clot in the middle cerebral, the posterior, the anterior cerebral, well, there's nothing we can do to mitigate against it. So in terms of an arterial anastomosis, these are alternative ways to bring blood through. So then if you're trying to bring this blood in here, if you have a clot right here, sure, most of the blood that should go through it can't get through, but you have alternative means to kind of force at least some bit of blood through. That way we can mitigate some of the problems, right? So you can lessen some of this. By the way, the worst part about some of these anastomoses is that you don't know if you have them until you have a real problem, right? The people that survive those widowmakers, and you'll hear about those. I have a friend that kind of survived a widowmaker, and they're like, yeah, I had it when I was 50, somehow I survived it. Well, what happened? Well, he had some alternative arterial anastomoses that allowed them to at least bring some blood into the right or left coronary artery. If it wasn't for these anastomoses, and you just have, let's say, a clot on this guy right here, and there's no blood flow, well, that capillary doesn't receive blood, that area dies. Again, we don't really know until we have it. Now, with the venous anastomoses, it's not quite as good as an arterial anastomoses. We want to have as many arterial anastomoses as possible. We think that the more we work out, the more the heart actually starts to produce more of these arterial anastomoses. So then people who are in great shape have the ability, right? Because they're in good shape, they have more of these arterial anastomoses that are kind of activated and produced. So then if they have an issue, they're able to deal with it much better than somebody that did not have these. Now, venous anastomoses are just alternative means for drainage. Again, right, that's important, but not quite as good as our, alternative means of bringing nutrients in. Neural innervations of blood vessels. Small arteries or arterioles, innervated to the greatest extent. All right? It's kind of weird, but the vessels of the penis and clitoris are the only ones that are innervated by the parasympathetic nervous system. Weird, right? Because everything else, all the blood vessels in your branches of anyone that we can imagine, superior mesenteric, inferior mesenteric, right? They're all going to constrict or dilate in the presence or absence of epinephrine and norepinephrine, in the presence of sympathetic or lack of sympathetic output. But these are the only areas where it's parasympathetic that can activate it. So with sympathetic innervation, vascular smooth muscle is innervated by the sympathetic nervous system. Increase in stimulation causes smooth muscles to contract. In the blood vessel, it causes vasoconstriction. Decreasing the diameter of the vessel. In the GI-GU tracts, right, it causes then decreased blood flow in that area. Again, right, think about what happens when you work out. Where do you want blood flow? You want it to the muscles. So what we're going to do is, in some areas, we're going to vasodilate. Right? So the arteries that leads to the skeletal muscles, to the heart, to the brain, those dilate in response to sympathetic output. In the GI-GU tracts, the smooth muscles there constricts in response. That way we can constrict the blood flow and decrease the blood flow to the GI and GU tracts. In the process, we dilate the blood vessels that goes to the arteries of the skeletal muscle. Now you increase the blood flow there, so that you can keep bringing nutrients to those active muscle tissues. Decrease in stimulation or presence of certain chemical causes vasodilation. In other words, in the absence of sympathetic output, then you have more relaxation in the GI-GU tracts, right? So again, it's not that you activate the parasympathetic and then you increase the blood flow because you activate the parasympathetic, right? Well, in terms of smooth muscle in the arteries, there are no parasympathetic innervations there. There's no connection to the parasympathetic nervous system in the arteries and the smooth muscle of the arteries. So what happens then, right? When there is sympathetic activity, you constrict. When there's no sympathetic activity, you relax. So let's say you're resting and digesting, you're eating. What happens then? You want more blood flow going to your GI tract and GU tract. What happens? Instead of activating the parasympathetic, right, is the absence of sympathetic activity that increases blood flow there. Again, there's kind of that fine difference, right? Because parasympathetic activity doesn't go to the arteries, it is the absence of sympathetic that activates. Now this is kind of, I like showing you these graphs because we can see just how big and just how much blood is actually found in our bodies when we're at rest and when we're exercising. So in this picture right here, 65% of blood volume at rest is in the veins and the venules. Think about that. So when we say that our cardiac output, right, is at 4 liters per minute, and out of that 4 liters per minute, you got to remember what happens, right? Well, we're only pumping out, and we're only having blood pump in about 1/3 of the capacity. So almost 2/3 of our available blood is stuck in the veins when you're at rest, right? And the veins function as a blood reservoir. So as you're at rest, yeah, all right, we're only pumping 1/3 of the available blood that's in our body. Now, what happens when we start exercising? Take a look at this. All right, remember when I mentioned that when you are resting and digesting, that's at rest, right? What happens? At rest, cardiac output, 5 liters per minute. But more importantly, look at where we see the blood going. At rest, rest and digest, and what happens then? Less sympathetic activity to the GI tract, the smooth muscle of the arteries there. If you have less sympathetic activity, then there's less constriction in those arteries of the GI tract. What happens, right? 1/3, if you take a look at combined, the digestive and the renal system, urinary system, right? Half of your cardiac output goes into those 2 regions. Half of it. So 2.5 liters out of 5 goes to the digestive and the renal system. Kind of makes sense because you're resting and digesting. At the same time, it also kind of makes sense that you have to pee so much when you're resting and digesting, right? Because look at that blood flow to the kidneys. The more blood flow, the more urine you will produce. So take a look what happens in the muscle, right? At rest, only 1/4, right? 1 liter per minute, that's it. Why? Well, you're at rest, you don't really need to bring blood to that area. Now, take a look what happens when we start working out. When we start working out, the cardiac output triples here. And what happens? That muscle, all right, blood flow, went from 1 liter per minute to 12.5 liters per minute, right? That's a 1,200% increase in blood flow. Now, where do we take that extra blood flow from? Where does all that blood come from? That extra blood, because remember, right, here when you add it all up, it's only 5 liters. Now, 17.5 liters. Well, we got to get the blood from somewhere, right? Where does that blood come from? This area, right? When you start to work out, you start mobilizing the blood that was found in your veins. As you start mobilizing those regions, you start activating the skeletal muscle pump to bring blood from your lower legs into your inferior vena cava so that you can bring it back to the heart. Now you start mobilizing all that blood that was trapped in the veins. That's what accounts for that, right, increase in the cardiac output. Now what else? Take a look at the renal and the digestive system, right? Combined now, it is 1.2 liters for both systems. Just barely, right, less than what it was at rest for just a digestive. So what we have done at this point, when we activate and we have moderate exercise, we have increased sympathetic activity, right? We have increased sympathetic activity, it increases your heart rate, increases your stroke volume. At the same time, you mobilize the blood that was trapped in the veins. Now you have blood, more blood you can have flowing around your system. Now, what else happens? More sympathetic activity, that increased sympathetic activity causes the arteries, the smooth muscles that are found in the arteries that goes to your skeletal muscles. Those smooth muscles in those arteries relax in response to sympathetic activity. As they relax, you can have more blood flow to those muscles. That same increased sympathetic activity causes an opposite effect in the smooth muscles of the arteries going to your GI tract and into your GU tract. All right, so when I have sympathetic activity there, it causes vasoconstriction in those arteries. So then we can redirect that blood flow to the muscles. It's kind of crazy just how big of a difference that is, though. Right, aging of arteries, of the arteries. There is a difference between arteriosclerosis and atherosclerosis. Arteriosclerosis is a hardening of the arteries. Basically, I don't like even saying the hardening of the arteries. I would say that the elastic arteries, the elastic tissue of the arteries becomes less elastic. Think about a fragile rubber band, right? You guys have all used our models where we use a rubber band to kind of hold everything together, right? And those rubber bands, when they become fragile, all you do is just move it a little bit and they rupture. There's no more stretch in them. That's what happens when we have arteriosclerosis. The problem with arteriosclerosis is that there's no good treatment. Right? With atherosclerosis, where we have this fatty thrombus here, we can do a balloon angioplasty, right? Get in there with what looks like a little drill bit, kind of drill out that fat and suction it out and put a stent in there to keep it open. With arteriosclerosis, you can't do that. And usually, with arteriosclerosis, it's systemic. Almost all of your arteries start having this. And when that happens, you can't bypass all of your arteries. So you start having some massive issues where you cannot bring blood to the heart, you cannot bring blood to the brain. So this is one that I'm more worried about than even this. Because this one usually happens to one or two vessels, right? You have angina, you have pain, you may even have an MI, but you know it's just within a few of the vessels. This is usually, right, degeneration of almost all of your arteries, making them less elastic. And you can't bypass all those arteries. So when you hear of arteriosclerosis and atherosclerosis, they sound very similar. The treatment's different. The way they have that pathology is different. The cause is different. All right, last thing we'll talk about is this blood pressure. Relationship between pressure, flow, and resistance. And one of those rare instances I know where I will probably be using the board a little bit. So you guys have to see my arteries look like a tube, my nerves look like a tube, and my skeletal muscle. Guess what they look like? Tubes, right? So they all are very similar because all I can draw is a tube. So when we talk about pressure, obviously pressure has that letter P. Flow is weird, it's got the Q for flow, and then resistance R. Now, in terms of blood pressure, what is blood pressure? And by Wednesday, I want you guys to see if you can answer that question about what is diastolic blood pressure measuring. Because that is the hardest kind of question that so far